Right, welcome to Foundations and Applications of Humanities Analytics. Today we're going to be talking about something very central to the foundations of humanities analytics, and indeed central to the foundations of a lot of quantitative inquiry, and this is probability and the interpretation of probability, right? So as I was just saying, probability is the core of many humanities analytics techniques, in part because it is at the core of so many quantitative techniques used in so many disciplines. I'm obsessed with probability, right? In many ways, I consider myself a philosopher of probability. I just absolutely love the concept. And what I think is so fascinating about probability is that it is at once extremely simple and extremely complicated, right? It's very simple in that the entire mathematical theory can be stated using just a few concepts and axioms. You really just need the idea of a set, a subset, a function, and these three axioms, and you've more or less got everything there is to probability. You can write down the axioms of probability on an index card, no problem. On the other hand, it's very complicated in that once you start trying to apply probability theory to various real and sometimes imagined systems as well, there's just this cascade of nuance and special cases that make things very complicated very quickly. And this is why someone can do a math PhD focused on probability theory, despite the sort of fact that ultimately the sort of axioms and statement of probability theory is sort of easily written on an index card. Here we'll keep it simple in part because I'm not a math PhD, so I'm not really well versed in the sort of most esoteric and sort of far-fetched applications of probability theory, and also because we want to just get you guys up to speed on probability theory, get you folks up to speed on probability theory in a very sort of simple way that isn't going to require too much math, and indeed there's very little math in this presentation as well. I should also say that there is an accompanying set of notes to this presentation that I prepared that I would really encourage you to read. Like this presentation, they're mathematically fairly simple, but they go into a little more detail on some of the mathematical concepts. And I really see it as sort of a complement to this lecture. And if you're really going to dig more into this stuff, I would encourage you to both listen to this lecture, watch this lecture, and read the notes that I've prepared. So we'll start by talking about the history of probability in a very sort of potted, idealized, simplified way. So today, the probability theory that we use, the sort of what we take to be the formal content of probability theory, comes out of work published by the Soviet mathematician Kolmogorov in 1933. And his work was really building on stuff that had been done throughout Europe in the 17th through 19th centuries, especially in France. Paris, for a long time, was a real sort of epicenter of probability theory and work on probability theory by people like Cardano, de Fermat, Pascal, Laplace, and others. Most of these people were working on finding optimal strategies for games of chance. And again, I think it's not surprising that you have sort of the emergence of sort of gambling halls in places like Paris coinciding with some of this development of probability that's ultimately culminating in Kolmogorov's work. But it's worth noting, and very interestingly, that older work on probabilistic notions, in particular the kinds of work on finding all the different combinations of possibilities in some system, which is very central to probability theory, goes back much earlier than what we think of as the sort of foundational work on probability theory done by these sort of mostly sort of French and Italian and German kind of thinkers. And in fact, it's being done in a different place. It's being done in Iraq, what's now Iraq, and Baghdad, and particularly, we can go all the way back to the 8th century, and attempts by people like Al-Khalil to try and list all possible Arabic words, right? So that kind of combinatorial work, trying to find all the combinations of possibilities within some system, is much older than what we think of as the foundations of probability theory. And moreover, it starts from a place of thinking about text, right? Al-Khalil was interested in the possible combinations of words in the language he spoke, right? So there's this long tradition of using probabilistic concepts to think about the structure of language and the structure of text. And obviously that's relevant in a humanities analytics context. Nevertheless, there is still a puzzle here, right? Which is that yes, you have this sort of advances in probability theory going on in Paris at the same time as sort of gambling halls, and gambling is very popular with the aristocracy, but games of chance are still much, much older than any attempts to theorize seriously about probability. The picture here is of some dice from the Indus Valley, uncovered in archaeological excavations and probably made between 3000 and 2500 BCE. So very, very old by most standards. And yet we only get the axiomatization of probability theory in 1933 by Kolmogorov, right? And we can contrast this with astronomy. You know, humans have always been fascinated by the night sky, but that fascination has more or less always been mirrored by an attempt to understand the sky scientifically, right? You have people like Ptolemy trying to understand the sky scientifically. They're not always getting it right. There are models of the solar system might put Earth at the center rather than Sun at the center, but they're still trying, right? And yet we don't see this with probability and with this sort of idea of likelihood, even though we've been gambling for thousands of years, probably addicted to gambling for thousands of years, and yet we're not really developing a science of chance and a science of probability in the same way that we're obsessed with the sky for thousands of years, and indeed we're developing science to go right along with it. So this is kind of a puzzle, I think. Historically, it's an absolutely fascinating sort of problem to think about. Simon has actually sort of inspired me to think more about a particular answer, which may or may not be true, but it's worth positing here, which is that prior to the industrial manufacturing of gambling devices, and indeed Pascal, one of the people working on probability theory, was also one of the first people to actually build a roulette wheel. He was trying to create a perpetual motion machine, and in the process discovered what he took to be this sort of really fun gambling device. But prior to this kind of sort of industrial standardization of gambling devices, it may well have been that the best strategy for being a good gambler wasn't to sort of really understand how probability works, but rather to know the idiosyncrasies of the devices one was using to gamble, right? So imbalances in the weights of dice, a bias in a roulette wheel, things like that. And indeed, there might have been clues that one could pick up on, even if one didn't sort of own the dice, that would enable one to very quickly figure out what the bias would be that could make someone a really good gambler, right? But then, of course, as we enter an industrial era, and these gambling devices are starting to be made in a very consistent, industrialized way, this kind of knowledge suddenly becomes much harder to find. And even if you are good at picking up on these clues and finding idiosyncrasies in gambling devices, if those idiosyncrasies just aren't there in manufactured gambling devices, then that knowledge isn't going to do you any good as a gambler. And so it's only then, perhaps, that people start to turn to an understanding of probability and what probability can do for us as a way of becoming better gamblers, right? So it's just a possibility, right? Now, if it's true, it's really interesting because as we saw in discussions of the history of temperature, there we had people who wanted industrial quality standardization of manufacturing. So people like Wedgwood trying to make porcelain the same way every time, were then developing scientific concepts in order to help them do that. If this story is true, then what we have here are advances in industry happening without the science that are then inspiring advances in the science of probability. We're just getting good at making dice the same way every time. And it's only then that we're starting to think, okay, well, now that we can't sort of gamble by picking up on the idiosyncrasies of these dice, how can we best understand these systems that we've created in order to be the best gamblers that we can? So that's an attempt at a potted history of probability theory. And I would think that there's a lot more to be said there. And I would encourage anyone who's sort of inclined towards this kind of inquiry to maybe think about if they have some alternative ideas or some other ways of thinking about this, this material that could be very relevant. We'll turn now to thinking about what the goal of probability theory is in a way that goes beyond just maybe being good gamblers or whatever, where gambling could be casino gambling, but also should I take an umbrella or not? Is it going to rain later? But going beyond that to think sort of more generally about what it is that probability theory is even trying to do. And I think that at its core, one crucial aim of probability theory, and it's the one that we'll sort of stick with for this lecture, is this ability to enable comparative judgments about how likely it is that either an event occurs, a given process has a particular outcome, or a proposition is true, right? So if I say that the probability of pulling any heart from a deck of cards is greater than the probability of pulling any king from a deck of cards, then this carries the implication that the first event is more likely than the second, right? And these kinds of comparative judgments of likelihood are sort of very important in all different kinds of contexts. In particular, it's going to enable us to predict things, right? If I think that event A is more likely than event B, then I'll probably predict that event will occur as opposed to event A will occur as opposed to event B. We can also do retrodiction if we can figure out that in the past it was much more likely that A happened rather than B, that A had a higher probability than B. Even if we don't know which one occurred for sure, we can perhaps do history by sometimes maybe assuming that A occurred instead of B, especially if A is much, much more probable than B. We can explain things using probability. We can say, well, why did or will some event occur? Well, because it is or was more probable, right? And finally, we can control things using probability, right? We can arrange things so that the events we want to occur are more probable, and that can serve all kinds of useful purposes for us. And recall in talking about patterns, the way that I highlighted this sort of controlling role of patterns, that's something that can be understood probabilistically as well. And all of these sort of activities, prediction, retrodiction, explanation, control, and likely many others, are all central to both scientific and humanistic inquiry. Right? So what is probability theory? And here's the part where I would really strongly encourage you, I know I sound like a broken record, but strongly encourage you to read the notes that I've prepared, because I think especially for these slightly more logical and mathematical concepts, it can be really helpful to both listen to a lecture and read some notes. So that's what I'm encouraging you to do here. For now, I'm going to present probability theory in a sufficiently sort of general way that hopefully you can sort of grasp the basics that you need. But again, refer to those notes for a more sort of perspicuous presentation of this same material. Right? So we'll begin by introducing a set, and we'll call this set omega, right? Now, since omega is a set, it has elements, and these elements sort of can be anything, and we can use whatever symbols we want to write down these elements on paper, right, in order to represent them. But in probability theory, we'll take them to represent events, outcomes, or propositions, right? And in particular, this idea that the elements of omega are all the possible outcomes of some process is going to serve us really well in thinking about the basics of probability theory. So for instance, it could be that omega is the set containing the numbers 1, 2, 3, 4, 5, and 6, and that each element of omega, each of these numbers, represents a possible outcome of the roll of a die, right? So very simple sort of gambling procedure. For our purposes here, we'll only ever consider sets with finitely many elements. So sets where you can count each element, and then you'll eventually reach a point where you can stop counting and you've counted them all, right? A lot of when probability theory gets mathematically very interesting involves cases where you don't have finitely many elements, but instead have infinitely many elements. But we won't need to consider those here. And arguably, it's not necessary to consider those for a lot of the context in which we want to deploy probability theory within humanities analytics. Right? Now, a subset of omega is any set such that all of its elements are also in omega. Right? So if omega is again 1, 2, 3, 4, 5, 6, then the set containing just 1, 2, and 3 is a subset of omega. Omega is a subset of itself, right? Because any element of omega is of course also in omega. But the set containing 1, 2, and 7 is not a subset of omega. Why? Because 7 is not in omega. And so the set containing 1, 2, and 7 is not a subset of omega. For any set omega, we can define its power set. And we'll denote the power set using this curly p and then the parentheses around the set omega, and we'll call that the power set of omega. And that is a set containing all of the subsets of omega, right? There are a few important points to note about the power set of any set, right? So for any omega, any set, the power set of omega contains omega as an element, right? Because any set is a subset of itself. And so any set omega is going to be an element of the power set of omega, because of course the power set is just the set of all subsets of omega. And for any omega, the power set of omega contains the empty set, or the set that contains no elements, as an element of that power set. Why? Because the empty set, the set with no elements, is a subset of any set. And that's because, recall we defined it as subset as a set such that all of its elements are also in the set of which it's a subset. And since the empty set contains no elements, it's trivially true that all of its elements are in any other set, right? So the empty set is a subset of all sets, and therefore it's an element of the power set of all sets. I know that went a little fast. I'd refer you here to the notes as well for a sort of written down version where you can sort of take this at your paces, right? So if omega is the set of all possible outcomes of some process, then the power set of omega is going to be the set of all possible sets of outcomes of that process, right? And indeed, it's that power set on which our probability function is defined. So a probability function is just a function that assigns any member of a power set a number between 0 and 1. So it's just a way of sort of inputting an element of the power set of omega, and then what you get out is a number between 0 and 1. You can think of this as just sort of like an algorithm that takes as inputs elements of the power set, so a sum subset of omega, and outputs a number between 0 and 1. And in order to be a probability function, it has to obey the following 3 rules, and these are Kolmogorov's axioms. First, the probability of the full set omega, which recall is an element of its power set, has to be 1, right? And this makes sense if you think about omega as the set of all possible outcomes of some process. Well, if it's the set of all possibilities, then one of them has to occur, right? And so the probability of any element of the set occurring has to be 1. The probability of the empty set has to be 0. This makes sense too, right? The empty set contains no elements. And so if omega is the set of all possibilities, the empty set doesn't contain any elements of omega because it doesn't contain any elements at all. And so its probability has to be 0. And finally, if A and B are subsets of omega that share no elements, so they have no overlap, then the probability of the process resulting in an outcome in either of those two sets, A or B, has to just be the sum of the probability of the process resulting in the outcome in A and the probability of the process resulting in an outcome in B. Any assignment of numbers between 0 and 1 to the power set that satisfies these axioms is a probability function for our purposes here, right? And that gives us a lot of room, right? There are a lot of ways of doing this. We have a lot of permissiveness in constructing a probability function. And indeed, this combination of omega, its power set, and a probability function is called a probability space. And there are many different probability spaces that we can construct for any given process. So at this point, we have a lot of room in terms of what we can do with probability theory, right? And this is why we need to move to this question of how to interpret a probability function, right? So what we've just laid out is something like the grammar or the syntax of probability theory, right? It tells us the rules for speaking coherently about probability, but it doesn't tell us what anything means, and it doesn't tell us what we ought to say, right? I can give you the grammar of a language, but if all you know is that grammar and you don't know what the words mean, you're not going to be able to interpret anything, and you're not going to know what you ought to say if you want to say true things or if you want to communicate in a certain way. You're just going to be at a loss to use language to any end. You'll understand how it works, but you won't know how to use it, right? And in fact, because probability theory is so general, as I was just saying, the same probabilistic grammar, the grammar of the probability space, can be used to express many different things. And as long as that probability function satisfies the Kolmogorov axioms, we can interpret it however we like, and will still be in keeping with probability theory, right? So we have a lot of room with which to apply probability theory. Having said that, and I think in part because probability theory is so open-ended in its possible interpretations, there are some standard interpretations that are used a lot that are worth thinking about, and worth thinking about in a humanities analytics context as well. So perhaps the most obvious, and certainly one of the ones that you'll see the most, is the frequency interpretation. And this is often associated with the physicist and philosopher Hans Reichenbach, one of the early logical empiricists based in Berlin, part of the Berlin Circle, and which was related to the Vienna Circle, fled Europe like many of the logical positivists, and ended up finishing his career in the United States. We can interpret omega, as I've been doing, as a set of possible outcomes of a process. And then we can say for any subset S of omega, interpret its probability, so the probability of S, as the frequency with which the process results in outcomes that are in S, right? So to illustrate this, if the process in question is again just a die roll, and omega are these six possible outcomes, 1, 2, 3, 4, 5, and 6, then the probability assigned to 1, 2, and 3, let's say we assign 0.5, 1/2, 50% as the probability of 1, 2, and 3, 1, 2, and 3. But this is just interpreted as saying that half of the time, the die roll will result in a 1, 2, or 3. And in some sense, this is very reasonable. But there's a problem, which is, how many times do you roll the die, right? I could roll a die right now. Let's say I roll it 4 times, and it comes up, 5, 4, 2, 6, right? So now we've only gotten a result in the set 1, 2, 3 one time out of 4. So does that just mean that we were wrong to say the probability of 1, 2, or 3 was 0.5? And in fact, we should have said that it was 0.25 or 1/4 because it only came up in that set 1 out of the 4 times we rolled the die? Seems clearly not, right? You just say, well, you just haven't rolled the die enough times. But then how many times should you roll the die, right? And the answer that Reichenbach gives is, well, probabilities really should be interpreted as frequencies of outcomes in a hypothetical infinite series of trials, right? So the idea is if we rolled the die infinitely many times, that the proportion of outcomes in this set 1, 2, 3 would be 50%. It would be 1/2 of the time in this infinite series, right? But this is weird, Infinite series of die rolls or coin tosses or any kind of other process that we might want to use probability to talk about, they're just not things that we observe in the real world. Moreover, it's unclear how useful this kind of information about infinite series of events really is to us, as the famous economist John Maynard Keynes sort of famously said, in the long run, we're all dead. So why do we care what happens in the long run, right? And we're really talking about an infinite long run. Right? Now, it's true that under certain conditions, finite frequencies are good guides to the infinite long-run frequencies, but those conditions don't always hold. And even if they do, long-run frequency interpretations take us to weird places, especially when we want to talk about humanities analytics applications, right? So let's go back to Simon's example of the marriage of capitalism and democracy, marriage and divorce of capitalism and democracy, and consider the probability that an article in the New York Times written in 1934 contains the word capitalism, right? We can obtain a finite frequency, and that's exactly what Simon did. He just looked at all the articles written in 1934 and tried to figure out as best he could the proportion that contained the word capitalism, right? But it's strange to say that what we're estimating by doing that is the frequency with which capitalism would appear in an infinite series of New York Times articles written in 1934. It just doesn't feel like that's what we're doing when we do that project, is sort of estimating what would happen if the New York Times had actually written infinitely many articles in 1934. It's not clear what one has to do with the other, and it's not clear that that's really what we're after when we do this kind of inquiry, right? So we can move to a different interpretation of probability now. This is the propensity interpretation, and it's most commonly associated in the philosophy of probability with someone like Karl Popper, right? So on a propensity interpretation, probability statements don't, strictly speaking, communicate anything about the frequency with which events either hypothetically or actually occur. It's just a divorcing of probability from frequency, which may seem strange at first. But it becomes a little more intuitive when you get the sort of positive side of the propensity interpretation, which is that what a probability does on this interpretation is it measures the propensity of a single run of a process to result in a particular outcome. So in a die roll case, if we claim that the probability of 1, 2, 3 is 0.5 or 50% or 1/2, how we interpret that as saying, that the degree to which a die is prone to land on 1, 2, or 3 is 0.5, right? And this allows for comparative judgments, right? Because we look at 2 sets of possible outcomes, and we can say that the process is more prone to result in one than another. So we facilitate that kind of comparison of likelihood that's so central to probability theory. And it's arguably more applicable in this kind of case study, right? So we're estimating, we're using a ratio to come up with this probability that capitalism is discussed in a given New York Times article in a given year. And we can say, well, what that's really measuring is the propensity of an article to contain the word capitalism. So if we think of the process as any writer at the New York Times, it's in 1934, sitting down to write an article, that's the process. How prone is that process in general to produce an article that contains the word capitalism? That's what we're measuring when we sort of take the proportion of articles that do contain the word capitalism and then call that the probability. That's what we're trying to estimate anyway. But the propensity interpretation still inherits some of the same problems as the frequency interpretation. Just as finite frequencies are only so good a guide to hypothetical long-run frequencies, we can estimate a propensity using finite frequencies, but we often have little reason to think that this will exactly match the actual propensity. There are conditions under which we can be fairly confident that observed frequencies are sufficiently close to the propensity under certain ways of thinking about these things. And this is what a lot of statisticians sort of try and guarantee conditions under which we can get these kinds of this kind of confidence. But this is no different from a long-run frequency, right? There too, we have certain conditions under which finite frequencies are good guides to long-run frequencies, but those conditions sometimes hold and sometimes they don't, right? Moreover, just as no one will ever observe a long-run sequence of trials, right? In the long run, we're all dead, so none of us ever sees an infinite sequence of trials. No one will ever observe a propensity. But arguably, and I think worse still for the propensity interpretation as compared to a hypothetical frequency interpretation, at least an infinite series of trials, there's some sense in which we know what it is, right? It's just taking something we're already familiar with, a finite series of trials, and extending it infinitely, right? So we can at least have some idea of what that even is. I just don't know what a propensity even is, right? I don't think I've ever seen one. I doubt you've ever seen one. It's something that sort of adds a level of kind of metaphysical invention to our thinking about the world that goes beyond what we can even really conceive of, or at least have some sense of what it is. So that for some people is going to be a problem with the propensity interpretation. And this takes us to a sort of third way of thinking about probability. And I know that it's Simon's preferred way of thinking about probability in a lot of his examples. I'm not quite as convinced, but I think it is still relevant here. And this is the subjective interpretation, most associated with Bruno Di Finetti, who's over here, right? So suppose that I pick a random New York Times article from 1934. I'll give you $1 if it contains the word capitalism, but you'll owe me X dollars if it doesn't. What's the greatest value of X such that you'll take the bet? Well, on a standard model of rationality, if, for example, X is 50 cents, then you implicitly assign probability 1/3 to the effect that the article contains the word capitalism. If you didn't assign 1/3 probability to that event, then you would not accept that bet, and you would accept different bets. And so it's by sort of eliciting this different kind of betting behavior from individuals, we can sort of figure out how strongly they believe that some event is likely to occur. For instance, if I would take a bet that pays out $1, but where I lose $100, I'm pretty confident that that event is going to occur, right? If I would take a bet that pays out $1, but only if the most I can lose is 1 penny, then I'm much less confident that that event will occur, right? And in fact, we don't need to worry about the mathematical details here. There are well worked out methods for figuring out exactly what probabilities you assign to events, given the gambles that you would accept and not accept on those events occurring, right? So this idea that what probability is really the degree or strength of belief, as can be elicited through gambling behavior, is this subjective interpretation of probability, where here probabilities really refer to the strength of someone's belief in some outcome, event, or the truth of some proposition, right? And then what frequency data does is it offers guidance on how we ought to bet given previous trends, right? So if you say, okay, the probability of a New York Times article written in 1934 contains capitalism is Y, then that's telling you something about how you ought to bet on a given article from that year containing the word capitalism, thereby also telling you something about what your sort of strength or degree of belief ought to be in that event that the article contains the word capitalism, right? But there are still problems with this interpretation, right? And I think the biggest one, sort of conceptually, is that by interpreting probability subjectively, we start to lose contact with the idea of there being a correct probability to assign to a given outcome, right? If the idea is that all probabilities are referring to sort of degrees of belief, then the question becomes, well, whose degrees of belief, right? Rather than there sort of being a truth out there in the world about the probability of some event. And without strong assumptions, I think it's hard to use frequency data to make inferences about the probabilities that one ought to assign to outcomes and the bets one ought to make. And I've put an image here of people getting very upset at the stock market crash in 2008 as just an indication that, you know, past returns do not guarantee sort of future returns, right? And this is going to be true. This is going to be a problem for all interpretations of probability, but I think it's especially a problem here where we're trying to make this normative link between what we observe and how we ought to feel, how we ought to think, right? And I think especially in humanities analytics, it's natural to think that what we care about are the nature of actual cultural processes and their likely outcomes. You know, when someone sits down to write a novel in a certain year, what's the likelihood that it's going to contain animal imagery or sort of floral imagery or things like that? Those are the kinds of things we care about. And we care about that more than how we now in the present day ought to feel about those processes, right? Because the subjective interpretation of probability ultimately says that probabilistic language communicates how I right now ought to feel about some process rather than the process itself, right? And I think this is a limitation of that interpretation in the humanities context, but we do avoid some of the kind of problems of the hypothetical frequency interpretation and the propensity interpretation in that we at least do think that these psychological processes of degrees of belief are accessible to us, right? They're there in our heads in a way that things like propensities or infinite trials just aren't accessible to us because they're very sort of strange sorts of abstractions removed from our psychology, right? So that's a definite strength of the subjective interpretation is its clear grounding and sort of more familiar human psychology, right? Now, I'm in favor of letting 1,000 flowers bloom, right? I think it's a mistake to try and find the correct interpretation of probability full stop. I think it said what's amazing about probability is that this fairly simple mathematical framework has a variety of interesting and potentially useful interpretations beyond even what we've discussed here. You know, moreover, it's rare right now in published humanities analytics for people to think about, okay, what do the probabilities I'm eliciting mean? How should I interpret them? But I think there's a rich amount of sort of more philosophically sort of rigorous work to be done thinking about how to interpret these probabilities. And I think in different contexts, frequency interpretations, propensity interpretations, subjective interpretations, other interpretations entirely may be relevant. And I think it's unsurprising, given this sort of richness of interpretation, that probability can be useful in understanding the nature of human cultural output, which is what we're trying to do in humanities analytics in all sorts of interesting ways, right? And so just to recap what we've done here in this lecture, we've given a potted history of probability while taking a guess at explaining this puzzling fact about the recency of the development of probability theory as compared to the oldness of sort of the things that probability theory is used to think about, such as gambling. We've presented the basics of probability theory, and I'll say between this lecture and the accompanying notes, I think I'm hoping I give you 99% of what anyone needs to know to understand probability rigorously. The rest is just sort of mathematically exotic extensions into all kinds of interesting contexts. It's mathematically fascinating, but I think in terms of just getting your head around the concept seriously, we've given you enough here to do that. I've discussed 3 possible interpretations of the probabilistic grammar, this sort of probabilistic syntax that we're developing, and evaluated their strengths and weaknesses, concluding that none of them, I think, is the be-all end-all, and that there's really interesting sort of conceptual work to be done in thinking more particularly in a given context, which interpretation of probability is more appropriate, right? So I'll stop there and thank you all very much for listening.